So I guess we get started. Let's see, a couple announcements. One is I came across an online book about Python, and it talks about patterns there. So if you want to read about patterns using the Python language, on the reading assignments, I put links to that book, and so the Python people might be interested in that. The second thing is, while you're busy working or not working on the current assignment, the problem becomes you may not be as interested in learning about more patterns that you're not going to deal with until later. So there's a material I want to talk about on coupling and cohesion, which comes from a book that was published a fair time ago, and it's actually, the book was very expensive when I bought it like 15 years ago, and it's even gotten more expensive, and the library doesn't have a copy. So I have, the material I'm going to cover comes from one chapter, so I put a copy of the chapter over to the library on reserve, and it's also on CalCopy, so you can go pick up a copy there. That,
What is this book?
There's a book on object-oriented software engineering. What's that? The name of the book, if you go to the syllabus, it's listed there. Is there any questions? Well, the visitor pattern needs a structure with different types of nodes. And that's what the interpreter pattern builds. So in problem 2, you're going to build a visitor that traverses the tree you build in number 1. Which does lead to the one pattern I want to cover today, the composite pattern. And the interpreter pattern is an instance of the composite pattern. And for motivation, a common example of the composite pattern is you have a GUI, right? And a GUI contains windows and sub-windows, and those windows contain basic widgets, right? Buttons and dials and text boxes and things like that. But widgets are different things than containers, right? Because containers, they hold things, whereas a button may have a callback and may have a label, but it doesn't hold things, right? And so the question is, if you build a program with the windows and sub-windows or containers and widgets, how do we store them, right? And so if you start doing it this way by having a collection of buttons and a collection of menus, I mean, it's not going to work, right? Because now when you're going to find something, you know what it is. And if you resize things, you then have to go through them all, and then your code starts looking like this sort of stuff, right? Where, well, you know, if I have update, then I have to go through all my buttons and tell them to update, and then I have to go through each one of the things, right? It's just, it's ugly, right? You know, so we're going to simplify things by saying, look, what we're going to do is we'll create an interface for a widget, right? And then all the concrete widgets will implement an interface, that subclass, that abstract class. And then we're just stuck with two of them, right? You know, then each method becomes basically two methods. You know, we go through my widgets and tell them to do things, and then we go through the containers and tell them to tell everything inside them to go through things, right? Definitely improvement. And that leads us to the composite pattern. Well, this is not it, right? It's close to it. Right? The composite pattern makes the container a subclass of our component. Which, strictly speaking, doesn't make sense, right? Because a container is not a component. It's not a widget, right? They behave differently, right? Containers hold things, and widgets don't, right? Widgets have actions you can perform on them, like press them and callbacks. Containers don't, right? But the point of this is I don't need this separation, right? Right, so with this component class that, you know, when possible, it may implement some behavior that all the components need. But the widget container has to re-implement everything because it never does anything directly. It only, you can operate on things it contains, but it, right? But then we get this, right? We can now unify everything by only need a component list, and it contains components and containers, right? And then my update is just go through and say update them all. And when you update a widget, it knows what to do. And a container then will just tell all its things it holds to update, right? And then it becomes, you know, since we're using inheritance slightly improperly just to make part of our lives convenient, it causes other problems, right? And the problems are, do you put container operations in the component or not, right? If you do that, then everything will be treated the same, right? It's just, okay, just go through and, you know, it's safer if you don't, right? Because, but then the problem is if you, at some point you need to know where the containers are, but you want to add something to it or subtract it from it, you need to know that is a container. Right? So there's no good answer, right? You can't answer the question. But it's engineering, right? We're trading off making one issue easier, but that causes other problems to pop up. So again, I think the basic idea is simple, right? Is that, oh, you have containers and things that go in containers, but there's certain circumstances when we want to treat them all alike. And so we use that crazy, right, inheritance to make the container a subclass of, the abstract class or parent class interface of component. And another issue is, so basically, right, you have your top container, and then you have subcontainers and widgets, and then containers of other subcontainers, right? And so that becomes like a tree structure. And sometimes an event may start at an individual widget at the bottom of the tree, but we need to propagate that up to its parent. So you may need to know, well, who's its parent? What are you in, right? Right. And so then you may need parent pointers, right? So when you add a component or an element, you just say, okay, but here's your parent, right? So if we start at the bottom, you can work your way up rather than just from the top down. And that's depends upon what you need in the context, right? Do you need that or not? And if you do that, then everything needs to have a parent, be able to have a pointer to its parent.
I'm sorry. So over here, when your button is extending the components, the composite pattern though has to assume that they're all the same, right?
Yeah, but they're not all the same, are they? And we could argue, should the parent pointer be in the parent, the abstract class component or not? But again, yeah, this inheritance, right, is slightly forced, right? And a container is not the same thing as a widget. Why would we do that? So we can do this.
It's complicating things more than just solving.
If we take Java as an example and look at swing, I haven't looked much at FX, but in swing, they use this pattern. They've got windows and they've got panes, and they're a subclass of a type of component. And they do that so they can actually do what I say, right? So you can do this. Now it makes you a little uneasy, right? I used to ask students, well, is it a problem when you build Java interfaces? But people don't do that anymore, so students couldn't answer the question, so why bother asking it? Because but there are times when it solves more problems than it creates. Yeah, I mean, who deletes components? Who, how do you, right? You want that, you want that parent class to know about containers. If you do, then all your widgets inherit container-like things. But like I said, this is one pattern which Java does use. Right? That's when you want to do it, is when, right, you want to be able to treat containers and individual items the same. Questions? So finally, we can talk about patterns in general. So this idea of patterns comes from a architecture professor from UC Berkeley, and he felt that people should be more involved in the design of their buildings, rather than having some expert over there tell you what you need. Like, they don't know what you need, right? But they know all the rules and regulations and what the structure can do and not do. So his goal was like, how do we get people involved in helping design their structures? And so he realized that people needed a language that they could use to sort of help formulate the design, right? And so he started creating his patterns, right? And so here's one of his patterns. So look, there are lots of times when you have to just wait, right? You have the dentist, or the doctor, you go to the airport, and you just sit. I mean, you have to wait until it's your turn, right? And it's like, it's just annoying because what can you do? I mean, for us, we look for the outlets. Okay, is there an outlet? Oh, there's one over there. I can go plug in and do some work, right? But other than that, I mean, what can you do? I mean, you watch the TV or read the old magazine. I mean, it's just like irritating, right? And so, waiting rooms, you don't. It's just so terrible. You go there and you sit, and the dentist brings in all their old magazines, and it's like they're 2 years old, and who cares? I mean, right? But but the problem is, how can you do something useful to you and still be ready when it's your turn, right? If you wander off, like, where are you? And you miss your call, like, well, sorry, we brought someone else. Now you're going to wait some more, right? Um, so yeah, bring them, find an activity that can be done nearby, right? So he mentions, look, in a pediatrics clinic, when you've got kids, right? I mean, they're full of energy, got to run around. So give them a little playground, right there, so that they can run around, and then when it's time to call them, you just step out and say, you come on here, right? Another example, horseshoe pit, or just some sort of place, right? Maybe another spot where people don't want to run around, but just rest or think or work, have a space, right? So these are his forces in his pattern, right? So And he actually produced several books in a pattern language, and they're like this thick, right? And it's rice paper, so it's, I mean, there's a lot, right? Um, and his goal was not to have a bunch of patterns, but a language we could use, right, to cover all these different situations in designing spaces for people. And then what happened is at one point he was surprised as he gets this call, and people say, "We want you to come and talk to our conference." And he goes, "Okay, that's great. What conference is this?" And he goes, "It's object-oriented programming." And they go, "I'm an architect. What are you guys crazy?" And they go, "No, no, no. You're famous. We read all your books, and we're modeling our work after you." And so he actually did go and talk about his work at a software conference. Um, so that's sort of the impetus for the name. And why doesn't it work? There's here's a pattern of education, and often there's two concepts related, right? To understand one, you need to understand the other, and to understand the second one, you need to understand the first one. So what do you do? If you just explain A first, and then it's like, well, but they're all confused because you know about B, but you don't know about B yet, right? And so yeah, it come up with this pattern of, well, you don't. What do you do? Well, you sort of make iterations, right? You vaguely describe A, vaguely describe B, and then you go back and give more details, and finally iterate and slowly build up knowledge so you can understand them both together. All right. So this idea of patterns has spread all over the place.
Sorry, I'm a little confused about how weighting has to do with patterns. So you're saying that like the observation of having someone just wait, they try to figure out how does that relate to patterns? Sorry.
Oh, how the rest of patterns as well. In architecture, this is a common situation, right? And so how do we structure our buildings to accommodate that? And so his pattern book is like, what sort of, again, like it's this thick, right? And there's hundreds and hundreds of patterns of typical things that people do in structures. And then how do we accommodate that type of activity, right? Another common one is everyone gathers around in the kitchen, right? I mean, kitchen is like a meeting spot. So why don't we design kitchens to meet that functionality, right? For a long time in this country, the kitchens are really small. It's like everyone wants to be there. So make them bigger and get rid of all, I mean, do you really need a big, huge living room when everyone wants to be in the kitchen? I mean, and so as the patterns of the typical types of activity that people could say, oh, yeah, I want this and this and this, and then we can now talk about how to design a building to meet those needs. So our design pattern book talks about two major principles that they use over and over again. One is program to an interface and not to implementation. And, for example, we use abstract classes or interfaces to define common interfaces instead of classes so that can be used to represent them all. And then declare variables or parameters or arguments to be of that type. So then we can swap them in or out. And this is something that Ruby people are familiar with. Well, what happens then is that gives you more flexibility because you're not saying, it has to be an array list. You're saying it could be a collection. So what collection do we use? Well, we can use one collection that meets our needs. And we can change later, and the code doesn't have to change. Right, and the collection hierarchy is a common example where we can say, look, okay, if we declare it to be a collection of students, then it could be an array list, it could be a vector, it could be a bag, it could be a set. Once we declare it to be an array list and start passing it around, and all the parameters are declared array lists, then changing that is going to be hard because you have to go find every place it's passed around, right? But if you look at, what's an appropriate higher level, we can, maybe collection doesn't work, but a set may work or a list may work, right? And so that's one of the design patterns. And yeah, and Ruby people talk about duck typing, meaning if it looks like a duck and it quacks like a duck, then it's a duck, right? Not worrying about, oh, I have to have, the duck has to be a subclass of the bird class, and it's just, if it's got the right methods, then we're good, right? And so those people are more used to this idea of, well, as long as this thing has the right methods, I can plug it in here, as opposed to, oh, it has to be a particular type. And the second one is, favorite composition over inheritance. And the advantage is composition allows you to change behavior at runtime, right? So inheritance is I create a subclass of A and add more functionality, but that again is determined prior to compile time, right? By composition, we mean, okay, class B, I'm going to have a field of type A, and then when I need that functionality, I can call a function or method on my field. And that's, when you look at the strategy pattern, that's what's happening, right? We can now pass in the strategy and change it, right? We're not fixed with having to say, oh, I'm going to call this method on the class to compare it to something else, right? No, I can change at runtime, getting a lot more flexibility, right? So these are the two design principles they use over and over again in all these patterns. And as we go through them, you should start looking for these, where are these design principles showing up? They also talk about designing for change, and they give things you may want to change, like algorithms, and they say, well, here are some patterns which will do that for us, right? So we've seen the iterator. Okay, the iterator allows us to forget about how you have to traverse through the structure, right? But it gives us some independence of algorithmic. The strategy allows us to pass in pieces of an algorithm, right? That gives us reduces some algorithm dependencies. And the visitor allows us to traverse and do different things, right? Not having to modify the structure. Inability to alter classes conveniently. Well, once a class is set up to accept the visitor, I can now add more and more operations on that structure without changing those classes. We haven't talked about adapter and decorator. We got more work to do, right? Dependencies on specific operations, so the command, right? The command worries about the particular operation, and so all the parts of the code don't have to, right? I can say, well, okay, I got the command, now just do or undo, right? Execute or unexecute. are not tied to the actual operation that the command is going to do elsewhere in the code. Chain of responsibility, well, yet more patterns we need to cover, right? Dependence on hardware and software platforms. Again, some patterns we haven't covered yet. But, how does Java work across different platforms, right? Like, you're supposed to write once, run everywhere. Tight coupling. So there's different types of things that we may want to build change in. And so there's a lot of those patterns we haven't talked about yet. There's quite a bit coming up. But there's a good list. I mean, you should find that in the text and remember where it is, because like, oh, I need, I've got too much tight coupling. What pattern might be useful? Oh, there's a list, right?
Question.
Hmm?
You ever run into like a situation where the design patterns conflict with each other, or you can't? I guess it's just this factoring problem at that point. Are there any common areas or common patterns that don't fit?
Well, again, for me, it's still engineering, right? Whenever we introduce a pattern, there's some benefits and some drawbacks, right? Things become more complicated when we add patterns. And the more patterns we add, the more complicated they get. And if you add enough patterns, it's just too complicated. So that, one of the authors of the book, Ralph Johnson, he was the only one that was actually an educator, worked at a university. He used to go out and, since he was famous for writing the book, people would pay him lots of money to go, teach programmers about design patterns. And so he had like a 2 or 3 day course. He'd go and offer for some large sum of money. And he said at one point he did one of these courses. And at the end, the manager, the organizer, the whole thing, has got up and said, I know you're all excited about all this new stuff we learned, but we need to go, very carefully. And Ralph's comment was, that was a real wise manager, right? Because, yeah, I mean, as engineers, if we learn new stuff, we got to use it, right? And if you overuse it, things get too complicated and too hard to deal with.
So more patterns isn't necessarily better.
No, more patterns isn't usually better, no.
Is it best practice to just take one and just stick with it then?
Look, your assignments are just tiny, right? Do you really need 3 or 4 design patterns in assignment 3? No. It's just there to give you practice, right? So it depends upon the complexity of your project and what do you need to have accomplished, right? What flexibility do you need?
In like an enterprise environment where you're actually writing code that's intended for production, I feel like, at least the way I tend to approach these kinds of problems, I feel like the apparent need for a design pattern would only present itself when I'm halfway done. I feel it, just in general with software development, as new to it as I am, it seems like you don't really know what the specific issues that you're going to encounter are until you actually get into it. Does that always stay the case, or is there a way of predicting what kind of pattern you're probably going to need.
That's a hard question. So the Agile development movement says, claims that people tend to be poor at guessing what they're going to need in the future. And so you tend to build in things that you never need and make your software more complicated. And then when you get to the point where you need something, you add in it here, but you made it harder to do because you've already added a bunch of
yeah, you're retrofitting code that's already poorly designed.
Right. And so there's a book out called Refactoring to Patterns, and they say, yeah, basically, look, what you want to do is just start without patterns. When you find you need it, then you refactor to add it. And again, Ralph Johnson says, yeah, there's only one pattern he will introduce right away, and the rest he waits until he feels it's needed.
Strategy.
No, template method is the only pattern he would introduce right away.
So when we're, is it best to keep patterns separated, like in separate classes from each other, or like better to combine patterns in one class?
Well, that's a hard question to answer in general. For example, the visitor pattern needs a structure of different types of nodes in it. And so often the visitor pattern gets used on a composite just because of the way they work. So often you see them used together, but there are different classes involved, right? If you do undo and you want to use a command pattern and there's one operation that's having an inverse, oh, how do you deal with that? Oh, maybe we add a memento to it, right? Just in that one case. But usually patterns solve different problems. And so it's not likely in the one class you're going to see 3 different types of problems that need 3 or 4 different types of design patterns.
Can there be a problem which cannot be solved using there is no best choice of a design pattern? Can there be a problem?
Sure. One problem is that the Gang of 4 book is so popular, people think there's only 23 patterns. But there's hundreds of patterns for different types of things. And again, the idea of a pattern is that people have found that people have used that solution in different situations. So the idea is just to try to encapsulate things that have worked in the past. But just because things have worked in the past doesn't mean we haven't come across all the problems of software development, right? Let's see. We talked about this a little bit a while ago. But patterns tend to start breaking things into smaller pieces, right? The strategy pattern is, the state pattern, which are getting smaller pieces. And so it's not a pattern, but it's something that helps lead us to some patterns. Lots of little pieces. And again, we start bringing in smaller pieces. Rates of change. These are hard to explain, but if things are changing a lot, for example, when we build GUIs applications, we want the view to be separate from the model. One reason is that we change the views a lot, right? I mean, you have a designer, no, I want this red, that's the wrong version of red, move it over 3 pixels, do all kinds of things to the view, right? Interface, but the model changes at a different rate. And so it's nice to have the view in one spot because then we can change it without having to muck with anything else. Right, part of the design principle, right, of programming interface helps us out, right? Because now we can interchange the state pattern helps us, right? We can change the state, we can change strategy, right? And this is a harder one, right? Can we actually move objects from one project to another? If we can, we've found some nice classes that are well designed. Slightly different topic. Coupling. So this goes all the way back. One of the first papers in software engineering was published in 1972. And this is when programming started to become big. And people were thinking, oh, we should be modular, but what's a module? What is it? And so Parnas wrote this little paper about the simple keyword and context experiment, right? And so you read, a bunch of lines, you get a file with lines of text, and then what you do is you take the line of text and you do a circular shift, right? So you take the first word and move it to the end, and so you get this whole long list of all these shifts, right? And just output them all, right? So circular shifts to all the lines, and this is sort of a project he worked on. Okay, how do we design this program, right? And so, the first solution they looked at was what do you have to do, right? And then each step becomes a module, right? And yeah, so you draw a little flow chart. First I do this, and then I loop back and I do this, right? And then each step becomes a module. And second solution was just worry about design. What design decisions you make you want to hide, right?
Is this related to rate of change?
Could be. I mean, it's just. Yeah. What changes might. Design decisions might be things that might be changed in the future, and it could be just this is really hard, so I want to hide it because I probably going to screw it up, right, and find some better solution later. And so they decide, okay, what you do is each module should hide some design decision, right? And then code it up in the language of time. And the paper said, yeah, look, solution one is more complex, it's harder to understand, and it's harder to modify. And so it was like, oh, and the first time someone said, how can we design better and don't focus in on, don't write this linear steps in your head. I do A, B, C, and D, and then code that up, but think about what can change, right? So in this case, how do you read the lines? Is it a file? Is it not a file? Right? What's the line? Um, and this, a lot of people will say, well, how do we know what, how do we know when this code is better than that code, right? Rather, we wanted some way of measuring that or something we could use to say, oh, this is better than that, rather than having some guru to go to and say, please tell me, based upon your N years of experience, is this good or not, right? Right? And so they came up with, various metrics, and most common, a couple common ones. One are coupling and cohesion, right? We're coupling this is the interaction of pieces in your system, right? And cohesion is, how well parts of the module fit together, right? And usually people say, well, you want loose coupling and high cohesion.
How closely is cohesion tied to how well your abstractions are defined? Like, because you said earlier in the semester, like, you want to have like one class per abstraction, more or less, right? And I'm wondering, is poor cohesion like symptomatic of poorly defined abstractions?
Yeah, of the two, cohesion becomes more subjective.
Okay.
Because how well the pieces related, right? Whereas coupling is like, well, this piece calls that piece, so it clearly they're using each other, right? Right, they're coupled, right? Coupling is more concrete.
Okay.
So I want to start looking at coupling. Now, when you go to the typical software engineering textbook, you'll find like a page, and they'll describe coupling and cohesion, and they'll have a paragraph on each one. And for me, I'm going, those are nice words, but when I'm writing code, I want something that tells me, what do I do, right? And if you don't give me something that I can, some measure understanding, where I can say, okay, I'm going to do it this way because, right? And actually, Parnas's paper, I still find useful. Like, okay, what decisions am I making here? Oh, I should hide it, right? Because I'm deciding whether I should do it A or B. I can do it 3 different ways. This way, oh, okay, that's a decision. So, okay, that decision should be hidden. That's something I can actually do concretely, right? As a rule I can apply while I'm writing code, rather than saying coupling bad, cohesion good. So. So years ago, I came across this book. It was actually this author Berard. He, in the beginning of the Obi-Wan phase, he was quite active on news groups, and he had posted these really long articles. They'd go on. Usually a news group article is like a screenful. His would be like 30 screenfuls, right? They were the major essays, and eventually he compiled them into a book and published it. And it's the only place where I found, a detailed description of coupling cohesion. And the weird thing is, he was not an academic, right? He worked in industry. He ran a consulting company. But his writings on the surface seem very, very academic, because this is what he has, one chapter on coupling cohesion, and there's probably like 500 references for that one chapter, right? And he's continually putting footnotes, and it's like, But he's a consultant, right?
The references would be all in the text itself.
So yeah, coupling is just a measure of independence among modules, right? How well are they tied together or not? And if you get uninterrupted coupling, right, that ties them together, it limits the reusability because if they're too closely tied, I can't take this, I take them both, right? And also, the more coupling, right, the more change over here is going to propagate, right? And so our design goal is we want the coupling, right, to as weak as possible. And he talks about the same level of abstraction, right? You know, so if you're building, you know, the software to navigate the space shuttle, it's a huge project, and a button object is a pretty low level, that's right. And so we're not worried about the coupling between the button and some higher level, but between the same levels. And now, he says as weak as possible, right? If we have a module, whatever that is, in our system, which has no coupling to any other parts of the program, delete it. Because if there's no coupling, no one's using it, right? And so I should be able to delete it, and my system is now smaller and still does everything it did before. So we can't get rid of coupling. And so he goes through and he goes through the literature and he says, look, here are various forms of coupling he's discovered. And he ranks them from weakest to most desirable to strongest. And then he has content coupling, which is he didn't know where to put, so he just put it off to the side. So what is static coupling? You know, it says output one module is input to another module, right? And of course, a lot of literature you looked at was pre-object oriented, and so he's like, well, here's what I saw then, but here's what it looks like in the whole world. And so basically the output of one module, and so it's you're passing in parameters or you're getting things back, right? So it says the common occurrence is, yeah, object A passes object X to B, and so then B and X are coupled, right? And so if you change the interface to X, then B may change. So, you know, here is, you know, I have some sort of method and you pass in something of type X. And so then, you know, our class B and X are coupled because we're going to use it. We're going to call methods on it, right?
There are contexts though where strong coupling is like appropriate, right? This is just kind of a guidelines and overview. Like this is something you should generally avoid, but there are cases when you want strong coupling.
Yeah, the goal is as weak as possible, right?
Sure.
That doesn't.
As possible being the operative words.
Right, because there'll be contexts where they have to be coupled, right?
Okay, yeah, definitely. Because I was thinking about my iterator from.
No, the iterator is tightly coupled to the structure, right? It only works in there. You're not going to reuse it.
And that's exactly how I did it. And I was like, oh no, did I do something wrong?
No, but that's. I mean, your iterator has to know how to go through that structure, right?
Right.
And so it's not going to work in any other structure. That's it.
Right.
But it does then allow the client code to be independent of the structure, right? Mm-hmm. Because now I call the iterator and it goes through the structure for me, and so the rest of the code now is less coupled to your structure. right? Even though this is the lowest form of coupling, we have to be careful, right? So yeah, what happens? I pass object X to B, and X contains sub-objects, and then B extracts a piece out of X, and now the problem is B is now coupled to something inside of X, right? Right. So as soon as I get something out of it, right now, and what's even worse is that when we look at the public interface of hidden coupling, we see that some type is there, so we know they're tied together, but we don't see that another type is involved. And so if we change another type, then it's not.
But you should have just known both immediately passed on some type of.
Right. So an example of this is sorting, right? So we want a general purpose sort that can sort by different things. And so we have some sort of student record, and then we have, get name. And now I want to be able to add those student objects to a sortable list and sort them, right? How do we implement that? Something you should be familiar with, right? So one way is, I can create my sorted list, and instead of, I'm using object instead of generic. But then when I actually add something, I need to know where it goes, right, to make it sorted. So how do I know that? Well, as soon as I, give me your name, we're in trouble, right? Because now I'm tied to an internal structure, right? And what happened was I said, well, names are sort of tricky because of the first name and last name, and some countries write the first name first, and sometimes do the family name first. And how do you compare? And there's a last name, the family. First you do the family names on the first name. And so now, maybe we need a class to do with names, right? Now what do we have to do? We have to, right, go inside of students. Instead of sorting the name of the string, we change that. Now internal change to the student, right, has percolated into our sort algorithm. Like, that's bad news, right?
It's still a problem, right? It's still a problem because that X don't get name acts like a Y, which we were talking about.
Yeah, so the change, right, in terms of students percolated out, right? And the first week we talked about, object program is good because it localizes changes, right? So not good, right? So we could, right, since all students have some sort of method to compare each other, right? And then, okay, this is better, right? Because now we're only tied to the public interface of the things we're adding, right? So there's less coupling, right? So it's better, right? But it's still not as flexible as we want because we want to be able to sort the same objects on different, right? And we would have to change that less than method on the class, right? And that can be a mess. But also, we're still coupled to, right, the explicit class of student record. So we can, create some interface that says, here's how you compare objects. I mean, Java has their own, but at least the names are more reasonable than 1, -1 and 1 and 0 and what? I mean, really? Yeah, I mean, the comparator is like, it's like, that's C stuff, right? I mean, get over it. You know, then we're going to student record, implement it, and then when we add it now, we add, right? Now we're programming to an interface, right? Programming to interface gives us more flexibility because now I'm not stuck to student records. I'm coupled to the interface, right? And now we can have concrete classes that actually implement that particular interface, right? So again, there's different, I mean, so that coupling has changed, right? From being tied to internal structures of the class, we change it, then we have to change our sorted to, oh, now I'm just coupled toward, right, the public interface of that interface, and now multiple classes could implement that interface.
So then, for us, that's good then to have coupling with the interface. Like that'd be ideal. Like if you're making any sort of coupling, to just use an interface that way you can extend it.
In general, it's better, right? Because now I can pass in, I can have a sorted list of student objects. I can have a sorted list of inventory items, right? Of different. So all of a sudden, this sort of list becomes more useful, right? Because as we know, this is still not flexible enough, right? It's still,
The implementer is still powerful or coupled to that parameter.
right. So we have another interface, it's something similar, but, right, instead of acting on, we pass in two objects, right? And then, you know, then we pass in a comparator, right? Basically a strategy pattern. And now, you know, we can use a comparator to actually, right? And we're still coupled to an interface, right? But our, our sort list is now more usable, right? I can actually sort the same items differently, right? Do we always need that flexibility? Not necessarily, right? But when we're sorting, right, we do want that. And then we can, right, create different comparing things, right, by name. And now these classes get coupled tightly, right, to the things we want to compare. But we only use them, right, when we want to sort that particular thing by name, right? So the tight coupling here allows the rest of the system to be looser coupled and more flexible. So we haven't gotten rid of that tight coupling, but we've isolated it into a spot where it's easy to swap in or out. You know, and then we can start, you know, create different sort lists by giving different strategies and change the strategies. And then, of course, with lambdas now, you know, we can use the comparator interface and use the comparator, right? And then we want to do it, right? You know, then our tight coupling is only in that lambda, right? We don't need to create a special class that again, we've further narrowed down where that tight coupling is, and the rest of the system still remains flexible. right? So even though data coupling is the loosest form, right, we can still have it too tight to make things not flexible enough for our needs. So we have to be careful about how we do it. And then people call it a functor pattern, where functions that behave like objects. So this came early, particularly in C++ when you're wanting to pass functions around instead of objects. And so yeah, so lambda sort of becomes an example of this, and then it becomes, well, why are you calling it a pattern? Because we do it everywhere. But just because it's common doesn't mean it's not a pattern, right? And actually, if it's really common, then it probably is a pattern. Using lambdas to pass around to do work for us. So we just call them lambdas, right? So this next type of coupling that's stronger is we call it control coupling. And so it's passing flags around to control what you do, either passing a flag in or returning a flag. And yeah, I mean, so you pass in a parameter and it tells you what to do, right? And so an example was the lamp, and you can turn the lamp on, you turn it off, you make it blink, right? And so you pass in an integer, and then depending on what the value of the integer is, it either turns it on or off or on, right? And then create a new lamp, and then we can call set lamp. And now here the coupling is the outside world has to know what values I can pass in and what they do. We have to know that 0 turns it on. We have to know that 1 turns it off, and 2. And so the outside world has to know the internal workings of that method to know what to pass in. Which is bad, right? Because now if I change how it works, then the outside world has to know, right? And remember, one of the goals was, object-oriented programming was you hide decisions inside of modules, and then the outside world doesn't have to know. But here, we do have to know, right? What are the values? 0, 1, -1, 5, what do they do? And of course, creating the static things helps, because at least now I can look there and see what the values are, right? And then I can use a compiler to make sure that I don't pass any illegal ones, but there's nothing preventing me from doing that, right? So he says the cure is, well, just break the operation into separate pieces, right? So have an on and off, right, and blink functions. And now, right, that's part of the public interface, and so the public world knows what we can do, and so we don't have to guess that 3 is blink. Right, so now it's on, blink, right. And you might even add like a toggle, right? So if it's on, turn it off, if it's off, turn it on, etc. And so that gets rid of that sort of hidden coupling between the internal workings and the outside having to know what does -1 do? Don't know, right? Is it? Why? It doesn't change any behavior, right? I'm not controlling the behavior. It's doing the same thing, right? No matter what I pass in as a float, the function is the same thing.
So it's not.
It's not control coupling, right? Control coupling is I pass in a parameter to decide what to do, right? What about this?
It's still doing withdrawal. It's still doing itself.
It doesn't actually tell what to do, right?
Yeah, I'm not passing a negative amount or a large to tell to do what to do, right? I'm just saying, here is the withdrawal, and is it, if it's valid, want to do it. Otherwise, tell me it's wrong, right? We're not passing the amount to try and control what it does. That's not the intent, right? So this is not control coupling.
So the intent to control it is
Right. Control coupling is, the intent is I pass in that 1 to turn the light off. I pass in 0 to turn it on. I'm trying to control it, right? Here it's just, I want you to withdraw. And doing a withdrawal depends upon whether you have the funds to take their money out or not.
So you don't want to hard code anything. You don't want to hard code the 1 and the 0 with the light on or off. Hard coding is better.
The hard coding is bad, but also the intent here is just do a withdrawal, right? And there are different situations that can occur, and you have to handle them all. That's not the same thing as passing in a 1 to do this and passing a 2 to make you do that. So what if the lamp had 50 settings? Do we have 50 methods?
I guess no. Preferably not. It can be avoided because it's just more code to maintain, more code to read. How distinct are these settings? Are we just talking about like brightness level 0 to 50? Strobe. The light is on or is off.
The issue here is, right, we want the coupling to be weak as possible, right? But that doesn't mean we can avoid control coupling all the time, right? If there are 50 or 100 settings, it's like, well, that's just too much, right? Why create a separate function for each one? Then you have to remember what they are. Okay, so we're just going to pass in something, and here's integers 1 through 50 or 1 through 100, and too bad, but so we'll make them constants, and so we can use the names, or maybe even create a enumerated type, right, which contains all the, and then we pass in the enumerated type, and use that, so we get, compile time checks. What's that?
The correct values.
Yeah, only the correct values go in, and they can give them names, and so that we're not dealing with 1 through 50. It's
But then, like you said, that goes back to the original problem. How will the user know, right?
Well, if you have a enumerated type and you give them all names, then the names tell us, right? We can't get rid of coupling completely. And so we have to, when you say weak as possible, we have to understand what that means and when we can reduce it, when It's important to reduce it because it's too brittle. We can't get the flexibility we need or want.
Would we prefer having multiple searches or equals in just one method in such cases?
Yeah, and that's what you're going to do, right? I mean, you're not going to do if statements, 50 of them, right? It's a switch statement in the 50 cases or 100 cases or whatever it is. But so next time we'll talk more about control coupling.